a question for you. What is the area under the curve? X squared plus y squared equals 9. And we're looking at the area in the first quadrant. There's a way to do this with no calculus. How? Leo.
Would it be like 1/4 times pi r squared?
Because this is the equation for a circle whose radius is 3, whose center is 0, and we want the quarter of the circle. So this area can be found directly. But even knowing the answer, I could ask you for a different way to figure out this area using calculus. If I wanted to do this using calculus, I'd start by rewriting the equation. So y is the square root of 9 minus x squared. And then I'd say, oh, that's the curve. I want the area under it. So I also know that this area is the integral from 0 to 3 of the square root of 9 minus x squared dx. Wonderful, perfect, beautiful. I now know the value of that integral. But what I don't know how to do that integral with calculus. Because if I said compute this integral and didn't give you the picture, my first reaction is, oh, let's do the fundamental theorem of calculus, and that means I need the antiderivative of this. What do I do?
You'd be able to take the square in big terms, so we get 3 minus x.
Unfortunately, I can't distribute a square root like that. Can't distribute square roots because they are chain rule style applied to the whole thing. I can't take the square root of each part. Jacob? Okay, if I wanted to do chain rule, then I'd say use substitution since I'm doing it backwards, right? So what's u? And then du is the derivative of that, which is negative 2x, crap. I don't have an x out here. The 2 I can deal with not having, the negative 2 even, but there's no x. So I'm missing the x here. If I was just missing the number, I'd be good. But missing that x means I can't convert everything to u properly. So maybe I could do an integration by parts piece on that. That would be a really ugly approximation, and I'd be here for a very long time trying to do that. I could, absolutely. But that won't answer this question, will it? That'll only answer this question. I already know this answer. I don't know this one. And so I'm stumped for a moment. And I say to myself, this sucks. Even if I try and do this with integration by parts, my issue becomes even more troublesome because then u has to be either that term there, the square root of 9 minus x squared, with dv being dx. And then when I do the derivative and give you another square root, that's going to make it worse. I'm not sure I like that. However, I also see sitting in here a circle. And if I've got a circle, maybe I can think of that circle in trig functions. So let's try a different kind of substitution. Instead of doing u equals, I'm going to do x equals. Here's a new kind of substitution. I could pick either sine or cosine, but the reason I picked sine is because the derivative of sine is plus cosine. If I picked cosine, the derivative of cosine is minus sine, and I have extra minus signs floating around, and that bugs me. So I picked this because it's got a nice derivative. But that's the derivative with respect to theta, so that's dx d theta, which means when I write it as a differential, I put that d theta on the other side. Now, you may be asking yourself, why the fuck would you do that? Let's take that expression for x, plug it into our square root. Wait a minute. 9 minus the quantity 3 sine theta squared. 3 sine theta all squared is 9 sine squared, right? So this like that. And now I jump back in my head to Friday. And I remember things we were using on Friday. Nora, what thing was I using that's going to work here?
You want to take out the 9 or you want the sine?
Leo, now they're multiplied. So I can take the square root of each part. The square root of 9 is 3. Square root of cosine squared is cosine theta. And all of a sudden, I don't have any roots to worry about anymore. You sneaky booger. Now, this square reduction idea actually makes my life a lot easier and brings me from a problem I had no idea how to do exactly to a problem I did Friday. Let's go back to the integral itself. The integral of square root 9 minus x squared dx. We know the square root of 9 minus x squared becomes this. And we know dx is also in terms of theta. If I take those two 3's, put them together and stick them out front, I have 9 times the integral of cosine squared theta d theta. I'm pretty sure we did the integral of cosine squared as our example on Friday, didn't we? Maybe we did sine squared, I don't remember which one. But all of a sudden, I've turned this into an integral I now know how to do. It requires one of my reduction formulas, the cosine of 2 theta formula, square reducing formula. I think it's on our trig formula sheet as. So I say to myself, okay, wait a second, over here off to the side, because I can never remember which one it is. So if I want it in cosine squared, I'll replace this. So I get 2 cosine squared theta minus 1, cosine 2 theta, rearrange, cosine squared theta is 1 plus cosine 2 theta all over 2. You're welcome to memorize that formula. I can't to save my ass. I have to rederive it every damn time. So now this integral is 9 halves 1 plus cosine 2 theta d theta. But I know how to do that integral. Yay! What's the integral of 1 d theta? Yep. I'm doing my integral with respect to, It's a theta, not x. Important to keep the variable straight here. Exactly. What do I do with the cosine of 2 theta?
That would be like minus 1/2 sine of 2 theta.
I got to do a u substitution in there. In here, I say u equals 2 theta, du is 2 d theta. Do we have a 2 next to our d theta? No, so I'm going to get a 1/2 sine 2 theta. Wait a minute. The derivative of sine is cosine, so there's a plus, not a minus. Let's see. Okay, that is 9/2 theta plus 9/4 sine 2 theta plus c. I've done my antiderivative. There's just one problem. My answer is in theta. I don't want my answer in theta. I want my answer in x. So the question is, how do I get back to x from here? Oh, I go back and I use the same substitution we used before, which was x equals, what did we write down earlier? Okay, so over here I'm going to write, remember that x equals 3 sine of theta, or x over 3 is sine theta. Which means if I want theta, I do the inverse sine. Great, I now know what to do with this theta. What do I do with this? I have written right over there, sine of theta equals x over 3. Draw a triangle. Draw me a right triangle and label it according to that statement. Oh, I'm all the way back to the very beginning of trig, which was what, 2-3 semesters ago, a year ago, long time, right? So I go here and I say, all right, if this is what I'm using to define a right triangle, one of those corners is going to be my angle theta. Which two sides of my triangle are x and 3? Yeah.
Would that be like the horizontal one?
Here?
Yeah. Or maybe the.
Which one is it? Oh, wait a minute. Sine is what two parts of my triangle?
The opposite.
Oh, opposite. Oh, so the hypotenuse is the 3 and the opposite side is the x. Rip back out Pythagoras for me. We have one side of my right triangle that doesn't have a label on it. According to Pythagoras, what's the label for this triangle, this side of my triangle? Oh, yeah. B squared, right? A squared, B squared, C squared, right? So whatever this thing is, that thing squared plus x squared is equal to 3 squared. Wait a minute, that means that that thing squared is 9 minus, well, doesn't that look familiar now? Which means that the side here is the square root of 9 minus x squared, exactly the same expression that showed up in my original problem. I'm now going to blow all of your minds again with more trig. Reason it's a prereq for this course, I promise. We can't just throw it out the window and ignore it. Sine of 2 theta, there's a double angle formula. What's the double angle formula for sine of 2 theta? I told you back when we did the trig stuff on Friday, there were only 2 double angle formulas I remembered. One was for the cosine, we've already used that. The other was for the sine. Sine of 2 theta equals. Yeah. 2 sine theta cosine theta. I have a right triangle. I know what sine of theta is. From my right triangle, I know what cosine of theta is. Based on this right triangle, 2 sine theta. What's cosine of theta in this right triangle?
Square root of 9 minus x squared over 3.
Ladies and gentlemen, you did it. Now, over in that right set of parentheses, here, we can do a bunch of canceling. I've got a 9 out front. I've got over 3 and over 3. Those will cancel. I've got a 2 here and an over 4. So I could do one more layer of simplification. And get a correct antiderivative. Holy. Like I said at the start of this problem, I don't know how to do this integral. I would never have expected to get a trig function out of it until I say to myself, wait a minute, the derivative of that inverse trig, that's on our formula sheet, the one on our Canvas page. Go to that formula sheet for me. Or go back to page, what was it, 354, chapter 4, section 9 in the textbook. Your choice. What's the derivative of the inverse sine of x? Tom, you're looking at that page. Did I tell you the wrong page? Is that the antiderivative one? All right, then go to the beginning of chapter 5. It should be right at the beginning of chapter 5. It's not the beginning of chapter 4. 5, section 3, 2, wherever the fundamental theorem of calculus is. Or if we pull the formula sheet off of our Canvas page, which I happen to have in front of me, so I'm going to use that for the moment. Hey, wait a minute. That sine inverse, its derivative has this square root. We got that doing the inverse derivatives, the implicit derivative stuff back in chapter 3. And I said we'd never have to use it again, but it links roots to trig functions. And that's my surprise connection here. To get around a root, I end up with an inverse trig floating in the middle of my problem. Yes, sir.
So I was thinking if you did cosine theta, that question mark divided by 3, then you can multiply the cosine theta by 3, now you'd be like, that size question mark.
Yes, exactly. And that's how we solve for that question mark, using this rather than end up with a question mark floating around in our final answer, right? I wanted to express it in terms of x. And that's why I went through here to find out what that side was in terms of x. But it turns out that it's always the expression from the root in our original problem. And that's where, if I go all the way back to the beginning, that's where the 3 came from in the first place. When I started this problem, all I had was the square root of 9 minus x squared, and my brain went, well, what the hell am I going to do with that? And that's why I put a 3 there, so when I squared it, it would match up, and I'd be able to reduce this. Which means whenever I see a problem that involves a root like this, without that extra x on the outside, my best bet is to make the substitution a sine theta. No matter whether it's 9 or even if it was 7, then I'd have a square root of 7 floating around in the problem for A. I'm not thrilled with that, but it would work. The key statement here is if I see the square root without the extra x on the outside, I stole the following problem directly from the textbook. And when I first saw this problem, I said, oh, look, square root of a squared minus x squared. Let's do the problem with the trig substitution. I'm going to go through and I'm going to say, okay, x should be 2 sine theta. And I did the entire problem. And then I went, wait a minute, there's an x cubed on the outside. So I'm going to have to not only use that x inside, I'm going to have to use it outside as well. This is not going to be fun. So I start by saying, all right, then dx is 2 cosine theta d theta. And now this turns into a giant integral involving a whole lot of thetas. I get parentheses 2 sine theta all cubed. Square root of 4 minus parentheses 2 sine theta squared. And then on the outside, I have 2 cosine theta d theta. Doesn't that just make me want to barf? That's disgusting. And by the way, I did the entire problem this way. And then I went to present it in class. I think this was, 5 or 6 years ago. And one of the students said, do we have to do it that way? And I said, well, how else would you do it? And the student said, that's an x cubed. Pull off 1x like we did by pulling off that 1 extra power in the sines and cosines. Now, why is that something that makes me happier to do? Now I can do a use of. I did the entire problem the hard way because I didn't think to pull off the extra x. But that's what we were doing on Friday. We were pulling off the one thing when it was an odd power. So I was very impressed with that student. I said, absolutely, and let's do it this way, and it's much faster. Because then I say u is 4 minus x squared, du is minus 2x dx. I don't have a minus 2. What do I do with that x squared? Yes, Dave.
If you want to put it outside the integral set.
I can only move numbers across my integral sign. I can't move variables. Promise you, we did this in the use subsection last week. I'm going to cheat and use my substitution again. Rearrange this equation to get x squared all alone, and we get x squared is 4 minus u. And now this integral becomes the integral of 4 minus u times the square root of u times negative 1/2 du. And that's a power rule problem. I take the minus 1/2 outside, and then I write 4u to the 1/2 minus u to the 3/2, and that's a whole lot easier to deal with. If I only had an even power out there, I wouldn't be able to pull that extra x off. And then I would have to do the trig substitution. If I had that odd power, I can do a regular u substitution. Here I get 4 times 2/3 u to the 3/2. Here I get 2/5 u to the 5/2. And then there's a plus c on the outside. Negative 1/2 times 4 times 2/3 is negative 4/3 u to the 3/2. Negative 1/2 times negative 2/5 is positive 1/5. And now I go back and put in my substitution. Minus 4/3 parentheses 4 minus x squared to the 3/2 plus 1/5 parentheses 4 minus x squared to the 5/2. So, in spite of the fact that I have a new trick, don't let the new trick prevent you from still using the old tricks. Questions? For the record, if you did it this way, you would get the exact same answer. It would be about 3 or 4 times as much work, but you'd get the exact same answer. Yes, please. That's the unfortunate side of that this version only works when I have the ability to pull out that du that Jacob was looking for earlier. We didn't have it. This time we have it, so I can use it. Other questions? All of this behavior hinges on the fact that I can simplify my square root using that trig identity. And the identity I was using up here was the fact that this would then turn into a cosine squared. Sorry, a cosine. When all of it was done, I'd have a square root with an a squared and a cosine squared, and that would be simplified. Problem. The identity I was using was the Pythagorean identity. The identity I was using was the fact that sine squared x plus cosine squared x is equal to 1. And so I was able to rewrite, 1 minus sine squared. If I try and do that here, and I say x is, well, we used theta up here. If I say x equals 2 sine theta, what happens here? What happens in the square root? Just work that part out separately like we did in the previous example. What do you get? Let's try it. Now, following what Nora told me earlier, I factor out the 4, and then I get sine squared theta minus 1. What's sine squared theta minus 1? Theo?
That'd be like cosine squared theta.
Go back up here and rearrange this to get sine squared theta minus 1. What happens?
It'd be negative cosine squared theta.
Oh, Houston, we have a problem. I don't want to do complex numbers here, much less try and do complex numbers in the middle of my integrals. The square root of a negative, because cosine squared is always positive. That's the square root of a negative. That's giving me something with an I in it, and no, just no. I don't want to deal with that. So I don't know how to do this. This is not going to work this way. And the problem is that it's sine squared minus 1 as opposed to 1 minus sine squared. There are some very, very rude things in my head at the moment. But one of them is actually helpful. This is the problem. But there were 2 other versions of the Pythagorean identity. There was the one involving sine and cosine, and then there was another one involving tangent and secant. What was that one? I'm not asking you to recreate this out of whole cloth. We did this last week. It should be in your notes. In Friday's discussion of doing trig integrals.
Tangent squared x plus 1 equals secant squared x.
So if I move this 1 to the other side, I get tangent squared x is secant squared x minus 1. That's in the right order. So what if instead of using sine, I used secant? What's the derivative of secant theta?
It'd be secant theta, tangent theta, d theta.
2 secant theta, tangent theta, d theta. So now let's look at that square root of x squared minus 4 again, and we'll do this substitution. And that gives me 4 secant squared theta minus 4. Now when I pull out that 4, what do I get under that square root? I get a tangent squared. So I was able to get rid of the square root this time, but the result is not an integral in cosines and sines, but instead an integral in tangents and secants. So the integral that I started with was the integral of x squared minus 4 over x to the 4th dx. Let's do this. On top, I'm going to get 2 tangent theta. On the bottom, what am I going to get? Yeah?
Would be 16 secant to the 4th of theta.
And then where the dx is, I have to put the expression for dx. 2 secant theta, tangent theta, d theta. And now I'm back to Friday again. Only this time my integrals in secants and tangents. Now, I will say that I really am not thrilled doing integrals in secants and tangents. I much prefer doing integrals in sines and cosines. So I'm actually going to take this and try and simplify the hell out of it all the way back to sines and cosines. Let's see what we can do. I've got a 2 on top. I've got another 2 on top. I've got a 16 on the bottom. Canceling gives me a 4 on the bottom. I'm going to write that 1/4 out front. I have 4 secants on the bottom. I have 1 secant on the far right on the top. Canceling that gives me 3 secants on the bottom. And I have 2 tangents. I thought it was a real fire alarm, people, and I was going to say, are we out the door down across the street?
Sorry.
Okay, in the future, set that to vibrate. Wow. 2 tangents gives me a tangent squared and a d theta. I look at this and my brain starts to hurt. I don't like that Even the stuff we were doing on Friday had tangents and secants multiplied together. These are divided. That pisses me off. I'm going back to sines and cosines. Tangent. Tangent is sine over cosine. So that makes this tangent squared sine squared over cosine squared. Secant. What's secant?
Like 1 over cosine cubed theta.
But it's in the bottom,
Yeah.
so I can bring that up to the top,
And then you invert it.
and that'd be a cosine cubed. Hey, wait a minute, I have a cosine cubed on top and a cosine squared on the bottom. Those cancel. Oh, goody. I know how to do this one. Whew. Worked, master, it worked. Yes, Renfield, here's the fly. What do I do from here?
I can do a U and D substitution.
U equals sine theta, D equals cosine theta, D theta. Please notice I have now done two different substitutions. So when all is said and done, I got to undo them both. The antiderivative of u squared is 1/3 u cubed. I have that 1/4 out there, makes it a 1/12. Undoing that gives me 1/12 sine cubed theta. How do I get from theta back to x? What was the equation between theta and r? But secant is secant of, right? So that theta is attached to the secant. What did we do with the sine? To get back to x, in the previous problem, the first one, how did we go back from theta to x?
Using the inverse.
And I had to draw the little triangle to figure out what that inverse was, right? So I go back here and I say, oh, secant theta is x over 2. And Leo just told me that secant was 1 over cosine.
Yeah.
So that means the cosine of theta is 2 over x. Now I draw a little triangle. If that corner is the angle theta and cosine is 2 over x, one of the legs and the hypotenuse, right? Cosine is
The x part would be 2 over the hypotenuse x.
adjacent over hypotenuse. What's the other leg? The other leg by Pythagoras is the same square root expression we started with. Hey, wait a minute. Based off of this triangle, what's sine of theta?
It
Lou?
would be square root of x squared minus 4 divided by x.
Which means this is 1/12 square root x squared minus 4 divided by x all cubed plus c. Whoa. So here's a sneaky thing. If my square root is subtraction, I'm either going to use sine or secant. All of my s's stay together. In both of these cases, I am subtracting. It's just which order I'm subtracting and tells me which way I should use sine or secant. And for the record, it took me forever to find that little memorization trick. Questions? Absolutely. Take the derivative of this, which is a chain rule and quotient rule disgusting nightmare, right? And make sure we get back, after a lot of algebra, that. Is that convenient? No. Does it work? Yes. Do I want you to do it that way? No. Easiest way to check your work is to check it in Wolfram Alpha. I don't see anything wrong with that, as long as you've done the work first. One of the big problems is that a lot of online sources for doing integrals just give you the answer, and they don't tell you anything about how they got there. Some will, if you pay for the service, provide a step-by-step version. Don't spend extra money on this class, people. No, I'm showing you how to do it. Let's assume the computer's not stupid. But it's also important to remember that there are algebraic simplifications that could happen. And if they do some of those, their final version might not look like our final version. Other questions? There's only one other thing that could be a problem here. I'm not subtracting in this problem. Stomp around cursing furiously. Nope. I'm going to be much happier because I'm adding, and I already saw a trig version with addition in it right here. Only it's the other way around now. The tangent is what's being added, right? So if I've got the x being added, I want the x to be the tangent. So if I'm doing this problem, I'm going to want x to be 2 tangent theta. And the easiest way for me to remember this one is because it's a plus sign, looks like a t anyway. So there are 3 basic cases. If I'm doing subtraction, the order tells me whether I should do sine or secant. If I'm doing adding, that's a t, use the tangent. Everything else we do is going to work exactly the same way. As long as the problem I'm doing looks like something squared minus x squared, something squared, x squared minus something squared, or x squared plus something squared. The textbook has 2 examples, and they're beautiful examples. What do I do with that? The 4 is screwing with me. Well, it turns out you actually have several different ways you could do this, but I think the easiest one to do is a u substitution. Because then 4x squared is u squared. is example 6 in the text. Example 7 looks like this. And that's just nasty looking. Until you do completing the square. I'm going to write this like that. What would make that a perfect square inside? So I add 1 here, but if I add 1, really with this minus sign outside, that's really subtracting 1, right? So I need to add another 1 on the outside. If you add it, you have to subtract it. Well, that makes this the square root of 4 minus x plus 1 squared. Do another u substitution. U equals x plus 1. And now it looks like what I want to do. You will see problems that kick us like this a lot. The problem is not doing the calculus part. It's getting the algebra and the trig to do the calculus the way we want to do it. So I apologize to you all thoroughly, but we need everything from 117 to 118, from algebra and trig, from all of pre-calculus, available to us. And unfortunately, there's no nice way around it. Questions? Tomorrow is our question and answer day. Our homework is due on Friday, 3 sections worth. Only the problems in the list labeled to turn in need to be given to me. I will answer any questions you have about these tomorrow. I also have posted already this example all typed up in several different versions. There are actually 2 different ways to do this problem. I think I put both of them on here. This is in the handout section on our Canvas page. We'll see you all tomorrow. Have a wonderful rest of your day.